So our fifth example is the double angle tension member. An ASTM A36 double angle 102 by 102 by 12.7 with 9mm separation has one line of 8 20mm diameter bolts in standard holes and is 7.5 meter in length as shown. The double angle is carrying a dead load of 180 kN and a live load of 530 kN in tension. Verify the member tensile strength. Assume that the gusset plate and bolts are satisfactory. So for ASTM A36, our yield stress is 250 megapascal and our tensile stress is 400 megapascal. This is the double leg 102 by 102 by 12.7. Yan. And it is separated by a 9mm thick gusset plate and they are connected with 20mm diameter bolts of standard holes. And we have 8 bolts with 7 at 75mm spacing, and our dead load is 180 kN and live load is 490 kN. So we'll try to solve the required tensile strength using LRFD. PU is equal to 1.2 the dead load plus 1.6 of live load. So our PU would now be equal to 1064 kilonewton. And for ASD, 180 kilonewton plus 530 kilonewton is equal to 710 kilonewton. Next, we will try to determine the available tensile yielding strength by solving the nominal tensile strength Pn. So our Pn is Fy multiplied by the gross area. Our yield stress is 250 megapascal and our gross area is 4,840 square millimeter. So our Pn is 1210 kilonewton. Under LRFD, multiply it by 0.9. We got 1089 kilonewton. Compare it with LRFD. The required tensile strength is 1064, so it is greater. Yan. Okay siya. And for ASD, the nominal tensile stress or strength divided by omega t. So 1210 kilonewton divided by 1.67 is equal to 724.55 kilonewton. And compare it with PA under required tensile strength with 710 kilonewton only. Yeah, so satisfied, okay siya. Next is to determine the available tensile rupture strength of the member. So, nominal tensile strength Pn is equal to the tensile stress multiplied by the effective net area rather. And for our shear lag factor, we will consider case number 2. All tension members except plates and HSS, so we will apply this one. And again, for case 8, single angle. If U is calculated per case 2, the larger value is permitted to be used. And since we have 8 fasteners here, we will consider shear lag factor would be equal to 0.8 for case number 8. Then compare natin siya sa case number 2, whichever is greater, yun yung gagamitin natin. So solving for the shear lag factor of case number 2, shear lag factor U is equal to 1 minus the eccentricity connection divided by the length of connection. So our connection eccentricity X bar, determine natin. So whether ano yung consider nyo dyan, whether the top or the bottom angle, parehas lang. So our connection eccentricity would be equal to the centroid along Y, which is 30 mm. So substitute lang natin. Our length of connection is 7 at 75 mm. So our shear lag factor is 0.943, and then for case number 8, yun nga nasabi ko kanina, we will consider 0.8 since we have 8 fasteners here. So whichever is greater, so mas malaki yung case number 2, so we will be using 0.943 as our shear lag factor. And for our net area, it is equal to gross area. Tapos tanggalin lang natin yung diameter and thickness nung angle. I mean diameter ng bolt multiplied by the thickness ng angle. So gross area minus yan. So 2 times in diameter 20 plus, remember, 2 millimeters multiplied by the thickness ng ating angle, which is 12.7. Our gross area is 4,840. So our net area is equal to 4,281.2 square millimeter. Now we are able to determine the effective net area. Multiply lang natin siya in the shear lag factor, which is 0.943. Our effective net area is equal to 4,037.17 square millimeter, sorry. And for our nominal tensile strength, our tensile stress is equal to 400 Newton per square millimeter. So our Pn would now be equal to 1,614.87 kilonewton. So under LRFD, we'll multiply it with 0.75. We got 1,211.15 kilonewton, and compare it with our PU, or the required tensile strength, which is only 1,064 kilonewton. Yan, okay siya. And under ASD, divide lang natin siya with our omega T. Would be now equal to 807.44 kilonewton. And compare it with PA. Mas malaki siya because our PA is only 710 kilonewton. Yan. And for the last requirement, we will determine the slenderness limit. Madali na lang yan. So, L over R, length of the total length of the member, divided by the radius of gyration along X. So, our radius of gyration is equal to 30.6. So our slenderness limit would now be equal to 245.1. And now we can conclude that the double angle that we design is adequate to carry the given loads.